today I want to talk about just a few sort of odds and ends left to discuss concerning logarithms. And first of all, a little something about logs with other bases. Last time we talked about exponential functions with other bases. Other than e. So the natural log is the log which uses a base of e, the special number e, but there are, as you probably already know, logs with other bases. I hope that you've heard of this before, but we'll just talk about it one last time just to make sure everybody is clear. So the natural logarithm comes from this function, y equals e to the x. This is called the natural exponential function. The inverse is this logarithm, which we call the natural logarithm, y equals ln x, all right? There are also exponential functions using a different base. So if I have the exponential function with base b, it also has an inverse, and its inverse is called the logarithm with base b. So this one here, the inverse, is called, well, I'll write it. It's written log with a little b down there, log b of x, and this is called the logarithm with base b, right? The log with base b. And its definition is it is the inverse of the exponential function b to the power x, all right? That definition makes it, that just saying it's the inverse is enough to be able to figure out what the logarithms of various numbers are. In general, you have to use your calculator to calculate the logarithm of a number. But there are some examples that you can do sort of in your head. Let me just say what it means that they are the inverses. So they are inverses. So what that means is something like if, y equals b to the power x, then x equals log base b of y. That's what it means when I say that these two things are inverses. It means if you have an exponential form, like these two things are just two ways of saying the same thing. And this is the way to say it in the exponential form. This is the same way, or this is the way of saying the same thing, but in a logarithmic form. It's just sort of the other way around. It's like if I say 2 plus 3 is 5, another way to say the same thing is like 5 minus 3 is 2. It's just a rearrangement and using a different operation. Instead of the exponential function, you use a log and you write everything in the other order. All right? So what that means is something like, this would be, typical homework problem or quiz question just about logs in general would be something like find these by hand. Like I said, you can do some logarithms by hand. For example, what is log base 2 of 8? The way to think about this is instead of writing it like a logarithm, write it instead like an exponential. So if I say log base 2 of 8 equals, then this is the same as, I'm going to write it instead of as a log, I write it as an exponential. It means 2 to the equals 8, all right? This is how you translate written in terms of a logarithm, you write it instead in terms of an exponent. And then, once it's written in terms of an exponent, you can sort of guess the answer. Can anybody say what 2 to what power equals 8? That's the question. 3 is the answer, yeah. So right there, it's 3. So that means log base 2 of 8 equals 3, all right? And if you're used to doing this, then you can sort of do all of this in your head. When you see log base 2 of 8, what that means is, what is the exponent that I need? 2 to some power equals 8, and the answer is 3. So that's the meaning of the logarithm when your friends at lunch ask you, what does the logarithm actually mean? It means something like, what is the exponent that you need in order to get something to some power equals something else? All right, some more examples. Of course, like if I ask you instead, what is log base 2 of 9? This is the same as 2 to what power equals 9? And that, I would say, I don't know. I mean, there is no nice number which has this property. If you need to know this answer, you would have to do it on your calculator. So this right here, I would say you can't do this by hand. All right. If I was asking you to do some of these on a quiz or something, I might say, like, I might give you a big list of these and say, either give me the answer or tell me that it's not possible to do it by hand. And this is an example where you can't do it by hand because 9 is not a nice even power of 2. All right. What about some other slightly weirder ones? How about log base 4 of 1 over 16? What is the log base 4 of 1 over 16? All right. I would say, think of this in terms of an exponential function. 4 is the base, so when I write this as an exponential function, this means 4 to some power equals 1 over 16, right? This little number down here becomes the base of the exponential, and it means that thing to some power equals 1 over 16. And then you have to figure out what should that power be. Anybody say? Yeah? Negative 2, he says. Yeah, because the answer here is a fraction, I hope everybody knows, the way to make a fraction from exponents is by using a negative exponent, because a negative exponent always means 1 over whatever the exponent. And so if you use negative 2, this will say 1 over 4 squared, which is 1 over 16. So here, the answer is negative 2. All right? So that means log base 4 of 1 over 16 is negative 2. Generally, the log of a fraction will be negative. Actually, we've already seen that for the natural log. All right. What about, here's another somewhat weird one. What is the log base 7 of 1? Again, I think of this in terms of an exponential format. This means 7 to what power equals 1? Any masters of exponents? 0. Yes, she is truly a master of exponents because she knows anything to the power 0 equals 1, right? So that is 0. And this is actually a fact of all logs. It's not, this actually had nothing to do with the number 7. This is not a special property of the number 7. No matter what this number is, something to the power 0 always equals 1. So it is a fact about all logs. The log with any base of 1 is always equal to 0. I'll write it this way. Log base b of 1 equals 0 for all base. Right? It's not a special property of the number 7 there. That is always going to be true. All right. These are logs with different bases. And like I said before, sometimes you can do these by hand, but more often you're just going to have to use a calculator to find the log with a different base. One objection that you may have immediately is my calculator probably doesn't have a log with a little b button. Typically, a typical calculator just has a ln button and sometimes a button that says log, but not with any little base written. So I will say, usually like on your calculator, you can calculate with a typical calculator. ln, there's a ln of x button, or what they usually write, just log of x. And when you see that log with no little number, this means, so this of course is the natural log, which we've talked at length about. This one is called sometimes called the common log. This is the base 10. So when you see log with no little number down there, what that means is log with base 10. So log x, when you see log written without a little number, this always means log with base 10 of x. The common log. In the old days, people used the base 10 log as kind of the standard kind of log. Nowadays, people don't really care about the base 10 log as anything special. The reason that people like the base 10 log is you can kind of estimate the base 10 log in your head. For example, if I do something like log of 100, can we say what's a log of 100? Log with no little base written means base 10, of course. Yeah? 2. It is 2. Yeah, why do you say 2?
Because it has a base 10, so it's 10 to the second power.
Yeah, right. Since it's base 10, what you should be wondering is 10 to what power equals 100? And the answer is 2. 10 to the 2 equals 100. So this is 2 log base 10 of 1,000. That would be 3, right? Because 1,000 is 10 to the power 3. And some number in between is basically going to be some number in between 2 and 3. You could say that this base 10 log kind of counts like how many digits are in the number, although it's one less. So this base 10 log sort of, I'll say, kind of counts how many digits are in the number. Like any 3-digit number has log 2, well, between 2 and 3. And any 4-digit number has a base 10 log between 3 and 4. And so the base 10 log is a lot easier to kind of estimate in your head. Like, for instance, if you ask me, what is, the log of 532,109? I would say this is, just because of how many digits there are, I know this is between 5 and 6, because there are 6 digits here. Probably closer to, well, I don't know, maybe somewhere in the middle. So this is between 5 and 6. So because you can sort of estimate this in your head a little bit at least, in the old days people preferred to use the base 10 log. Nowadays that everybody is going to do this using calculators, it doesn't really matter anymore. And so there's not really anything all that special about the base 10 log in this day and age, all right? You might say the base 2 log is maybe more important these days because computers run everything on base 2, and so the base 2 log is actually fairly important inside computers, at least, although ordinary people don't typically care about it. But anyway, how do we do the other logs on a calculator? So it is possible to do other logs on a calculator, even if your calculator doesn't have a button for the other logs, right? Your calculator has a ln button and usually also has a base 10 log button. But what if you wanted to do, say, the base 5 log? This is possible because of what we call, we call this the change of base formula. Right? Your calculator only has the natural log on it, but that's because they expect you to know the change of base formula. And so if you want to do some different log, you can easily do that if you know the change of base formula. And can we just try and figure out what that is? So this is a way of relating one type of base can be related to any other type of base with this fairly simple formula. Check it out. So if y is the log with base b of x, I would like to re-express this somehow in terms of the natural log, because my calculator has a ln button but it doesn't have a log base b button. How can we re-express this? Well, one way that you can do it is rewrite it in the exponential format. So instead of writing this with the log in that way, I'm going to rearrange things. It's going to say b to the power y equals x, right? This is the exponential version of that same equation there. And that thing on the right-hand side, we can do some tricks on it. So this, I am going to do ln on both sides. It says ln b to the y equals ln x. We can do some more tricks. Anybody remember the appropriate trick? You can do something on the left-hand side of that. There's a rule about the natural log. One of my favorite rules about the natural log. Anyone remember? We got rules in this house. Yeah?
So you move the y in front.
Yeah, move the y in front. So it says y ln b equals ln x. All right. Next I'm going to divide by ln b, and that's basically all we need to do. So it'll say y equals ln x divided by ln b. But check out what happens. I'm going to plug the original expression for y back in. Y is the log base b of x. So this is worth knowing. I'm going to put this in a box here. The log base b of x equals ln x divided by ln b. So this is how you do these other logs if you're using a calculator. So for example, if I really wanted to do log base 2 of 9, log base 2 of 8 is 3. I expect log base 2 of 9 will be like a little bit more than 3. But if I wanted to do this on my calculator, you would type it in like this, ln 9 divided by ln 2. All right, and the answer would, I don't know what the answer is, but something a little bit more than 3. All right, this is how you do other kinds of logs using your calculator. The change of base formula. And that's why your calculator only has the ln button. It doesn't have all the other ones. Yeah?
So should we bring our calculators on?
No. First of all, this is not going to be on the quiz tomorrow. And also, I wouldn't ask you to do this on your calculator on the quiz, because you're not going to use a calculator. Yeah. I mean, maybe on the homeworks you might want to do this, but maybe in your own personal life, if you're diagnosed with a strange blood disorder, you might want to do this. The quiz is Friday. Yeah, sorry. This is another argument I have with your question. Yeah. Yeah, the homework is due tomorrow. The quiz is on Friday. All right, great. Okay, one last thing about the log with a different base, and then we will be done talking about that. Let's talk about the derivative of the log with a different base. All right, everybody knows the derivative of the natural log, just to refresh our memory, is 1 over x, right? What about, how about derivative of the log with base b, right? The answer is it's going to be kind of like 1 over x, but also it has some extra little something involving the b, all right? And you can figure this out. We don't have to work hard at this at all, just because log base b of x is equal to that. You can just use the change of base formula and then take the derivative of that thing. So by the change of base formula, we can say derivative of log base bx. This is the same as derivative of ln x divided by ln b, right? Because those are the same. The log base b of x is the same as ln x over ln b. And now how do we do that derivative? You might say I have to use the quotient rule, which is a kind of a pain, but actually it's not necessary because the denominator has no x in it. The denominator is just a constant, which means you can make this a lot easier by just factoring the denominator out. Because it's a constant, I can just pull out the denominator like that. All right? And then what is the derivative ln x? I just said it's 1 over x. So this is, actually this is my final answer. I'll write this again in a big box. This is the formula for the derivative of a log with a different base. It is, usually I write it this way, 1 over x times ln b. All right, it comes from just doing the change of base formula and then taking the derivative. Make sure you put the x and the b in the right spot. It's very easy to mix this up and say 1 over b ln x, which is very different from 1 over x ln b, which is correct. All right, this is the derivative of the log with a different base. In particular, for example, if you ever need to do derivative log x, remember when no base is written, then the b is 10. And so this is equal to 1 over x ln of 10. And so on. All right. And this, I think, is all I wanted to say about logs with different bases. Any thoughts about that? There's not a whole lot to it. You just have to keep straight sort of where the b goes can be a little confusing at times. It's easy to mix it up. I think not so difficult. All right, great. One more thing to discuss concerning all of this exponential and logarithms business, and then we will move on to something completely different. I thought we should at least briefly discuss the number e as a limit. This, I'm not sure, is this is probably something that you've seen before in high school when you talked about this. Actually, the original discovery of the number e, or the first people to realize that e was an important number, they thought of e in terms of a limit of something, a special limit of something. We've been discussing e as a special value of the logarithm, but of course they thought of e first and then the logarithm later. So where did they come up with e if they didn't already know about logarithms? They came up with e as a limit. So I would like to So I will just say, historically speaking, and then I want to try and talk about how this connects historically. E was discovered as this. E, it turns out E is equal to this limit. And this is probably how it was originally presented to you in high school. Is that this is the value of the number E. It is that limit. When you think about the limit on the right-hand side, if you tried, like if you didn't know any better, you might just sort of try to do this limit. And if you look at this stuff on the right, taking n to infinity, that would make this fraction part 0, which would mean you're basically looking at 1 to the power n, which seems like it ought to be 1. But the problem is, at the same time you're taking n to infinity, the exponent here is becoming infinite. So this is like 1 plus a little bit to an infinite power. That seems like it's going to be infinity for that reason. And so actually the true value of this is, you know, somewhere in between 1 and infinity. And where is it? It ends up being this special number E, is this limit. This was first discovered by people trying to do calculations involving compound interest. If you've ever seen the formula for compounding interest, it is something that looks similar to this. So E is kind of a, if you say, like, historically speaking, pi was discovered by people doing geometry. E was discovered by people like doing capitalism. This is where E was originally discovered, although of course it's not, we are not slaves to the capitalist system by using E these days, but that was the first time that it was, that people started realizing that maybe it was important for something. Anyway, I would like to try to talk about what really is the relationship between this number, this limit, how is that related to E as we have been describing it so far. Remember, for us, so that's historically where it came from. To us, E is the number where E is equal to the natural log of 1. Like, that's what I said the definition of E is. E is the natural log of 1, where the natural log is some kind of area under the curve of something or other. All right? Now, what's the connection? Can we actually demonstrate that these two things really are the same? So the natural log of 1 really is the same as that limit. That's what I would like to try to connect. And this will just take a few moments of explanation. It has to do with the derivative. We all know the derivative of ln x is 1 over x, right? And if we write that derivative using the definition of the derivative, so this is something that we are basically never going to do in this class, but it's something that I'm sure you all did in your youth in Calc 1. So write this using the definition of the derivative. Sorry, I meant to say, sorry, so if f of x is ln x, sorry to squeeze this in, then f prime of 1, this is going to be important. What is f prime of 1? Well, f prime of x is 1 over x, and if I plug in 1, I get 1, all right? F prime of 1 is 1. But instead, I want to write this using the definition of the derivative. I hope that you have some space in your brain to remember the definition of the derivative, or at least remember that it is a thing that you once had memorized. This is the limit as, in our book they write it using an h. Sometimes this is written using delta x. Limit as h approaches 0 of f of x plus, sorry, and I'm using the derivative at 1. So it's really f of 1 plus h minus f of 1 divided by h, right? This is the definition of the derivative as a, instantaneous rate of change. This is the way you had to find the derivative before your teacher told you the easy way. This is sort of the hard way of doing it by hand. And you said, why I got to do that? Why didn't you tell me the easy way first? And they're like, no. It's good for kids to do this. It's true. It is good to understand how to do this by hand, but eventually you learn tricks. Anyway, I am using the definition of the derivative for one last time, the first and last time this semester. I'm just trying to see how can we do the definition of the derivative here. You know, you would plug in the f's, right? And in this example, f of x is ln of x. So this is the same as lim h goes to 0, ln 1 plus h minus ln 1 divided by h. One of those things in there can be simplified. Anybody got an idea? One part of this you can simplify. Yeah? Yeah, ln1 is 0. Great. Don't try to split this up. Actually, this cannot be split up. ln1 plus h does not split up. ln1 equals 0, though. So this, I can say, is the same as lim h goes to 0. Ln 1 plus h divided by h. And maybe I'll write it instead like this. 1 over h ln 1 plus h, right? And one last weird step, because of the rules of the natural log, if you have the natural log to some exponent, remember the exponent can come down front. I'm going to do the reverse here. This is actually the same as ln 1 plus h to the power 1 over h. All right, I'm doing that rule about log with exponents, but kind of backwards, making the coefficient into an exponent. Usually you do that rule the other way around, but just for fun, I'm doing it that way. All right. Anyway, we're pretty much done with this. I don't know if you like this kind of derivation or whatever, but you can see what we started with was f prime of 1, but I already said over here f prime of 1 equals 1. All right, maybe I should have written that at the very beginning. 1 is that. All right, so all of this together says 1 equals lim n goes to 0, natural log 1 plus h to the 1 over n. All right, and right here, I'm now going to write this in the exponential form. Yeah?
Why did you put it to the 1 over
Y is a, sorry, that should be a h. My h is kind of, does that help at all? There are no n's here. This is a h. Sorry about that. I got to make my h's taller. So this had a 1 over h in the front, and then I did that rule about the exponent can become a coefficient. I did it the other way around. The coefficient can become an exponent, right? It should have been an h. Sorry, no n's. Now she said, why did you do that? That's maybe a deeper question, and the answer is basically I did that because I knew that this was going to work later on. That kind of a step is a weird step, and there's no real good reason why you ought to do that, but it turns out to work in what we're trying to demonstrate here. All right, the very last thing is, this is a logarithmic format. I'm going to write this in exponential format. So exponential form. This says on the right-hand side, it has a limit there, but on the right-hand side it says the log of this equals 1. That means e to the 1 equals, and I'll put the lim over here where it goes, this. All right. The logarithmic form said the log of this equals 1, so the exponential form would say e to the 1 equals this thing. All right. And now that, if instead of h going to 0, I'm going to change h into 1 over x and make x going to infinity instead. So this is actually the same as e is x going to infinity, 1 plus x to the 1 over x. And that is what I said at the very beginning was the old school sort of historical limit definition of the number e, all right? This is the connection between sort of this is kind of like the full circle. The way that we have presented e and log is kind of backwards from the original historical way that they developed, but this is how they finally connect. This is the limit definition of the number e, all right? So maybe I could answer, I don't know, how interested you really were in the question, why did I do that step? Basically, it's because I know that this needs to be up here at the end and where I end up with. So this is why we put this this thing up there. I'm sorry, I wrote this, I just changed the variable to x. I meant to change h into 1 over x's because this is going to infinity now. It should be that. 1 over x inside and just x in the exponent. Sorry, I'm messing it up at the end here. Can you tell? It's because I'm sick of talking about exponents and logarithms. This is the last thing that I wanted to say about it. This is the full connection to the historical development of the exponents and the logarithms. Any thoughts about that? This number e does come up in real life, although not in my real life, but it comes up. All right, excellent. Here ends our discussion of exponential functions and logarithms. We are going to go on and talk about another important type of inverse function. So all of this business has really been one big important sort of category of inverse functions. The logarithms and their inverse functions are the exponential functions. Or you could talk about the exponentials first and their inverses are the logarithms, all right? There's one other important type of inverse functions that we are going to consider. And this maybe is something that you've seen before, but maybe not. Our next section is about what are called the inverse trig functions. The inverse trig functions. So these are things that you can see on your calculator. Your calculator has buttons that say, like, sine with a little -1. This is called inverse sine of x, or there's an inverse cosine and there's an inverse tangent. Those are called the inverse trig functions. I don't know if you've seen these before, but it's fine if you haven't. They are defined as inverses, and so you can use a lot of the same ideas that we've been talking about logs and exponents. Those same ideas can apply to these functions, the inverse trig functions. All right. So what this comes from, or like why you would want to use inverse trig functions, are kind of like if I have a triangle here and I know two of the sides. Let's say this is a 3 and a 1, and that's a right triangle. I'll use a theta here for the angle. The basic, like this is the standard question when you would want to use one of these inverse trig functions. Which theta goes there? Like what actually is the angle that is required if you wanted to make that right triangle? And the answer is, I don't know. I mean, this is too hard to do in my head. If I really had to do this in real life, I would use a calculator to do it. And the button that I press on the calculator is actually related to one of these inverse trig functions. So as for the question, what is the appropriate theta that goes there? I don't know off the top of my head, but you can say something about, from the picture here, we know that tan of theta equals 1/3. That's because, I hope everybody remembers your trig functions, the tangent is the opposite over the adjacent. So if you have such an angle, its tangent must equal 1/3. And so the question really is, what is the theta for which the tan of theta equals 1/3? And the answer is, that's what we use, the button on our calculator that says tan with the inverse on it. So tan theta equals 1/3. In this case, theta equals this inverse tan of 1/3. And that's what that button on your calculator does. It tells you what is the angle. So generally speaking, something like inverse tan of x means what is the angle whose tan is x, right? That's what that means. So on your calculator, you'll see an inverse tan. There's also an inverse sine and an inverse cosine button. And this is what they are meant to do. They tell you what is the angle whose tangent is whatever, or what is the angle whose sine or cosine is whatever. All right? These functions, they, on your calculator, they're usually written with the little -1 like that. These are also written like this, arctan of x. It means exactly the same thing. It's just another way of writing it. So sometimes it is written with a little -1. Sometimes it is written with the arc. They mean exactly the same thing. And then there's also arc sine of x, which is written also with a little -1. Pretty much on every calculator they use the little -1, I think just because it makes it like smaller so that it can fit on the button. But mathematicians generally prefer calling them arc whatever. So the arctan, the arcsine, and the arccosine are the standard inverse trig functions is what we call them. The arccosine has 2 C's in a row. It's true. All right. These are the inverse trig functions. There's also like arcsecant and arccosecant and arccotangent, but people don't usually talk about those. Let's not go crazy. All right. Now, there are kind of things we need to talk about with these. They are a little bit less straightforward than just saying this is the inverse of this. And the reason is because I will say these are not exactly true inverses. Because I will refresh our memory. For instance, let's talk about sine and cosine, arcsine. The graph of sine of x looks like this. Everybody knows, right? This is sine x. And, what we call the arcsine or the inverse sine, you would want to say it's just the inverse of that function. But there's a problem. Can anyone recall some basics of inverse functions? There's a problem with taking that and finding the inverse. Yeah? Yeah, this function is not one-to-one. It's like very much not one-to-one, right? Remember, one-to-one means that any horizontal line hits the curve only once. Here, horizontal line hits the curve infinitely many times, all right? So this is not one-to-one. And neither is cosine, right? Cosine looks basically the same as sine, but it's shifted over a little bit. And tan, I hope everybody remembers, the graph of tan looks something like this. It has these like recurring asymptotes. This is tan x. This is not one-to-one. None of them are one-to-one. Sine, cosine, and tangent, none of them are one-to-one. So technically it doesn't have an inverse. And this is what we need to talk a little bit about. Technically, it has no inverse function. And this is why I said these inverse trig functions, so-called inverse trig functions, are not actually true inverses because there is no such thing as the inverse function of sine x because it's not one-to-one. The solution to this, but of course, we want to be able to do this kind of thing, like this kind of question about, for instance, what is the angle in this triangle? Of course, that is a meaningful question, and it's the kind of question that seems to be something you would want to be able to figure out. So what is our solution to kind of make this work, even though these are not invertible functions? The solution is we choose an invertible piece of the domain. And this will look slightly different for each of the sine and the cosine and the tangent. You actually have to do this a little bit differently for each of these different functions. We choose an invertible piece of the domain. So let's talk about sine first. Cosine will be similar, but not exactly the same, and then the tan is a little bit different still. Let's talk about sine. So for arcsine of x, also known as aka inverse sine of x, we begin with the entire function, but I want to choose only a piece of it. So don't draw this. I will first draw the whole thing, and then I'm going to erase most of it. All right. That, of course, is not one-to-one. I want to choose a piece of it which is one-to-one. And I'm going to start at the origin and pick like sort of the biggest region around the origin. Like that much of it is one-to-one if I only look inside that box. But of course, we can make the box a little bit bigger. I think if you want the biggest piece of it, which really is one-to-one, you can go all the way up to here and back to here and take this much. All right. That's actually the only part of it which we could find the inverse of. Because if you sort of stretch that box any further out to the right, then it's not going to be one-to-one anymore, because these values will come back down and you're not allowed to have that. So this is the portion. I will make this, let's make it a little thick, the thickness. All right. Just that part is where we can find the inverse of this function. And it doesn't exist for anywhere outside of that specific domain. So this function, we consider, no more thickness. We consider only the domain. Now, if you think about where those values are, this is minus pi over 2 up to pi over 2, right? Those are the values. Those are the x values where those sort of tops and bottoms of the curves go. So we are considering only this domain, minus pi over 2 to pi over 2. And of course, the range of this, it goes up to 1 and down to minus 1, because that's what sine does. All right, we consider only that domain, and then just that piece of it, we can find the inverse. And you find the inverse, like the graph of the inverse would be by doing this sort of mirror image around the line y equals x. So we consider only this domain and invert that piece. And so the graph of the inverse sine, or the arc sine, looks like I take only that piece and do this sort of mirror image reflection across the diagonal line. So since I'm reflecting across the diagonal line, it means what used to be x values on this picture, they become y values. So, and what used to be y values on this picture, they become x values. So what I'm about to draw, the domain of x values is the original y value. So the domain now goes from minus 1 to 1. And the range goes from minus pi over 2 to pi over 2. And then the curve does this, this kind of sort of S shape, but it's actually the other way around. So it's going to do, it goes from here to here, but the curvaceousness is that way, because it's the original shape but reflected across that diagonal line. So it kind of curves in the opposite direction. All right, and this is the graph of y equals arc sine of x, also known as sine inverse of x. All right. Could I just say once and for all, this is very different from 1 over sine of x. That's totally different. And actually, that already has a name. That's the cosecant of x. So when you see this little minus 1 here, it does not mean 1 over. And that's maybe why, one of the reasons why mathematicians generally prefer to write it like arc sine, because it's not got anything to do with 1 over sine of x. It's a completely different function, only defined on this little piece. All right. Any thoughts about that? So anyway, we can do some values of the arc sine. If I just give you like random values, you basically have to use your calculator to find the arc sine of something or other. But there are certain values that we can do by hand. So for example, what is the inverse sine? So I'm going to write inverse sine sometimes I'll write arc sine. It all means the same thing. What is inverse sine of 1/2 equals? All right. you have to think about what that means. It means, what is the angle whose sine equals a half? Another way you could sort of rewrite this, rather than as an arc sine, write it as an ordinary sine. What I'm asking is sine of what equals a half? Any trigonometry masters out there? I'm asking, what is the angle for which the sine of that angle is a half? Anybody remember your unit circle values or something like that? Or maybe some shapes of special triangles? This is the way that yeah? Is it what? 3? 30. Oh, degrees you're talking. All right, I was like, why is she saying 30? That doesn't make any sense. 30 degrees, yes. Pi over 6 radians, in other words. I believe that's right, yeah. This, when I see 1/2, I start thinking about the 30, 60, 90 triangle. I just said 30, which is this one, right? This is the 30, 60, 90 triangle, and the sides go 1, 2, and root 3, right? I hope that everybody remembers that type of triangle. And what is the angle whose sine is a half? Well, it's the 30, because the opposite over the hypotenuse is 1/2 in this case. All right, so the answer here is, this is 30 degrees, also known as pi over 6 radians. I'm always going to write this in terms of radians, because that's the kind of guy I am. So that means inverse sine of 1/2 is pi over 6, right? And what does that mean? It means the reason the answer is pi over 6 is because sine of pi over 6 is 1/2. All right. So in order to do these values kind of in your head, you have to have a very good recollection of all of your standard values for sines and cosines. All right. What about the inverse? Well, we haven't. I was going to say, what about the inverse cosine? But let's talk about the graph of the inverse cosine first. What about? I got some more like this. How about inverse sine of 1? This means, what is the angle whose sine is 1? Anybody recall that? This, again, you have to just kind of know your values of sines and cosine. Yeah?
Pi over 2.
Yeah, that would be pi over 2 is the angle whose sine equals 1. So this is pi over 2, also known as 90 degrees, since sine of pi over 2 equals 1, right? This also, you could just like look at the graph. The graph of inverse sine of 1, you can tell that the when I look up 1, the answer, sorry, I'm scrolled a little. The answer is pi over 2. But the inverse sine of 1 is pi over 2. All right, great. What else? I got one more. How about, just for fun, I'll write this one as an arc sine. It means the same thing. How about arc sine of root 2 over 2? That means, what is the angle whose sine is root 2 over 2? Anybody recall this one? Yeah? That's pi over 4. Yeah, 45 degrees. So this is pi over 4. The 45 degree angle has sine of 45 degrees is 1 over root 2, also known as root 2 over 2. All right. What about, one more. Did I say one more already? How about negative root 2 over 2? This is an angle whose sine is negative root 2 over 2. How do you make the sine negative? The sine becomes negative in the fourth quadrant, right? So I would say this one is negative pi over 4. All right. The sine of a negative pi over 4 is negative 1 over root 2. Yeah?
Could you also say like 7 pi over 4?
This is a good idea. So this is actually what I wanted to mention in just a moment. So why is this true? This is because sine of minus pi over 4 equals minus root 2 over 2, all right? But, like he said, aren't there other numbers, sine of something else? Like, there are other values where sine also equals negative root 2 over 2. So I would say also sine of, what did he say? He said 7 pi over 4, which I like that, is minus root 2 over 2. And so can't the answer also be 7 pi over 4? And my response to that would be, well, first of all, this inverse sine is a function, so it just has one answer. It's not possible to have two different correct answers for the arc sine. And the where that was made specific is we specifically chose this piece of the function, which means when we do this arc sine, like 7 pi over 4 is out here somewhere. And so that means when we do this inverse, that never counts as one of the answers that we're looking for. So it is true that also the sine of this equals the same answer, but because of the way we define this in terms of just one piece of the domain, we always choose the piece that's in between minus pi over 2 and pi over 2. And we never choose the answer that's anywhere else. This is a strange technicality. That's really the problem, is that the sine function is not one-to-one. So you get weird things like this. So also this equals that, but 7 pi over 4 is not in the range minus pi over 2 to pi over 2. And that range is the only ones where we consider valid answers to the inverse sine or the arc sine. So it cannot be the value of arc sine of anything, right? We are dealing with only a small piece of the inverse because the whole overall inverse doesn't exist. Excellent. Thank you for that question. Since it's the inverse, we can do, since inverse sine and sine are inverses, at least on that little piece, on that domain, we have these sort of very simple properties. Sine of the inverse sine of x, anybody can even say what should that be? They are inverses. So what happens when you plug one inverse inside of the function? It's just x. Yeah, they cancel each other out. This is kind of what inverses mean. It means one like undoes the action of the other one. So this equals x. Now we have to be a little careful about this. I'm going to back that up. Sine of sine inverse of x. This is true whenever x is in the proper range, right? If you're plugging x into the inverse sine on the inside, this is only going to work when x is in this range, because that's the domain of the inverse sine function. So this is not technically true for all values of x, for all numbers of x, because say if I plug in x equals 2 here, this is undefined. So, and the other way around is true. If I put the inverse on the outside, this is only true when x is in the proper piece of the domain for sine of x. All right? So that second formula, the inverse sine of x, they cancel and you just get x, but that only works when x is in this small piece of the domain. If x is outside of that domain, you can actually plug it in over here, but you'll get a different answer from x. You get something like x plus 2 pi or something like that. And this is because of that issue with different values having the same sign. All right, so this is what happens when you plug sine inside of arc sine, or arc sine inside of sine. You can also do something like cosine of inverse sine x. This is something that's going to come up later on in the course, but it's interesting to talk about on its own. This can be simplified. Cosine of inverse sine of x. Although it's not a simple thing, you have to kind of work this out. And the way to do this is draw a triangle with angle inverse sine of x. All right? So I'm going to draw a right triangle. I'm just sort of making up the shape of it. I don't know if it's really going to look like that, but This is a triangle, and the angle of inverse sine of x. This is weird, but this is how you want to do it. I'm calling that angle inverse sine of x. Now, what is that angle? I don't know, but the only thing we know about that angle is its sine. So this angle here, the sine is x, right? The sine of that angle is x. That's what inverse sine of x means. It's an angle whose sine is x. And that means I can fill in some of the sides of this triangle. The sine is x. Of course, that's the same as x over 1. And the sine is opposite over hypotenuse. So I label the opposite as x and the hypotenuse as 1. This is because the sine is op over hyp, right? And so I can label the op is a x and the hyp is a 1. And then there's another side, the side on the bottom, which actually I don't know what that side is, but that side we can determine now using the Pythagorean theorem because we know the other two sides. So this side right here, maybe I'll just call that A temporarily. We can find this side with the Pythagorean theorem. It would say a squared plus x squared equals 1 squared, right? These are the two sides and the hypotenuse. And then that can be solved for a. I would subtract x squared. A squared is 1 minus x squared, and then take a square root. All right? So that's what the side on the bottom is. So I'm going to redraw my picture now that we know. I have x here, 1 here. The angle is inverse sine x. And the side on the bottom is this, 1 minus x squared. And now finally, I can ask, what is the cosine? Remember, all of this was trying to answer this question at the top. What is the cosine of that angle? So, cosine of that angle, it is from this angle the adjacent over the hypotenuse. That's what the cosine is. Adjacent is this, root 1 minus x squared over hypotenuse, which is 1. So this is, well, it's just this. Adjacent over hypotenuse. Here the hypotenuse is 1, so you don't get any denominator. All right. This, I don't suggest memorizing this as a formula, but this is true. The cosine of inverse sine of x equals square root 1 minus x squared. All right. What about, can we do the tan of inverse sine of x? Can we do that? So similarly, now if you hadn't already did this, you would have to actually go through the whole thing, build this triangle, but actually you're going to use exactly the same triangle. So if you are asked to do tan of inverse sine x, you would first draw the triangle for inverse sine x, which is that, and then you just take the tan of this angle here. Can anybody say what's the tangent going to be? I hope you remember your SOHCAHTOA thing, right? The tan should be opposite over adjacent. What's it going to be in this case? Can anybody say? Yeah? Yeah, you look at this triangle. This is the angle I'm talking about, inverse sine x, and then I do opposite over adjacent. That's opposite would be x, adjacent would be this guy, square root 1 minus x squared. So it's like that. This is complicated and weird looking, but it's not actually terribly difficult to work out, in my opinion. It's just something you gotta draw the weird looking triangle and then do the SOHCAHTOA thing to find the sines and cosines and tangent. So the cosine of inverse sine is that. The tan of inverse sine is that. I would say don't memorize these formulas. I mean, I suppose you could if you want to, but you should know how to figure them out by going through this little process. And of course, sine of inverse sine of x is just x, right? Great. I think we have 15 minutes left. That's enough time to just talk about the inverse cosine. So it's very similar to the inverse sine. It's just we should talk. You're going to see there is kind of an important difference, just in the way that we come up with the graph of inverse cosine. So let's talk about inverse cosine, also known as arc cosine. Same idea. We begin with cosine, but cosine is not invertible, so we have to choose only a piece of it which is invertible. So I'm going to start by drawing the sort of the full graph of cosine. We are going to pick only a piece of it. So cosine, remember, is the one that starts up top like that and comes down. And I'm going to choose only a piece of this where it is 1-to-1. Now, if we try to start off just like we did with sine, you will see immediately it doesn't work because, like for instance, if I take, say, a box like that around the origin, actually this already is not 1-to-1 inside the box because these guys have two values. In fact, if you are trying to define the arc cosine, you cannot use a box that goes around the origin because this little thing here is never 1-to-1 near the origin. So the solution is, instead, we use this as the domain. All right? That is 1-to-1 on that part of the domain. So this domain that I'm using in terms of x values goes, of course, from 0 over here, and this is x equals pi, just straight up pi, not pi over 2. And then the range here is, of course, 1 up top and -1 at the bottom. All right? And so that piece is what we use to define the arc cosine. So this curve is just the cosine. I am going to do the old reflection, sort of mirror image reflection across the diagonal line to make the arc cosine. So this is just cosine of x, right? The arc cosine, which I will draw down here, the inverse cosine if you like. It goes, so remember I'm interchanging the domain with the range. So the old one, the domain with 0 to pi, this time the range is 0 to pi, like so. So this range of x values becomes the range of y values, and then the original y values become the x values here. Sorry, I should have drawn this over there, right? My x values are going to go -1-to-1. And the curve has that same kind of a curvaceousness to it, but it's sort of opposite. So it begins like this. That's what the curve looks like. Sorry, that's not right. I'm having a bad day today. The curve begins at x equals 0, y equals 1, right? And so what I should be drawing should start at x equals 1, y equals 0. I'm trying to do the opposite. It starts here. It goes back the other way. Sorry about that. All right. The original graph contains a point like 0, 1. That means what I'm drawing here has to include 1, 0, which is there. And then it comes back that way. All right. This is the graph of y equals cosine inverse of x, also known as arc cos of x. All right. And it means what you think it means. It means what is the angle whose cosine equals whatever. All right. I want to say a little bit more about this, but I think maybe I would like to stop there and we'll just start up next time from here, if that's all right with everybody. All right. Let me know. You know, I have, like I said, I don't have my usual office time right now, but since I'm finishing a little early, I have, about 15 minutes now. If anybody wants to chat about the homework, I would be happy to. Otherwise, see you tomorrow.